All right, so let's talk about this inverse square. All right, so let's imagine we have this butter gun. Because, we want to butter our toast, and so we've got this melted butter we spray through a square opening, exactly this, size of a piece of toast, and the gun deposits butter 1 millimeter thick. And what would happen if we move the gun twice as far away? Well, if you did that, it's going to cover twice as much horizontally or vertically and twice as much horizontally, and therefore we're only going to get 1/4 of what we got. Let's take a look at a picture. This makes a little more sense. All right, so we've got this butter gun. Now, I like this, okay. There's a U.S. patent applied for this, obviously. Yeah, okay, funny. So we'd use this butter gun and we spray it on a piece of toast. And we spray it so that it's exactly 1 millimeter thick. And now if we move it farther away, or if the toast is farther away, that spray will continue to spread out. So assuming that you're not increasing how much it's coming out here, if you're going twice as far away, you've now gone 2 by 2, and so you have 4, the area of 4 pieces of toast at this point. So it's only going to be 1/4 as thick here as it was in the original. If you go 3 times as far away, it's 3 by 3. It is now 1/9 as thick as it was back then. This idea of things expanding in, inverse squares is pretty common. There are a lot of things that have that happen. This is known as the inverse square law. And you'll run across that in a number of different things. We run across it when we talk about light, radiation, sound. If you are 3 times farther away from the source of the sound, it is only 1/9 as loud as it was before. So all of those things kind of apply. So if we're talking about gravity and distance and our inverse square here, the greater the distance from the Earth's center, the less the object is going to weigh. So if we have an apple that weighs 1 Newton and we're at the Earth's surface, if we go twice as far from the Earth's surface, which by the way is a long ways from the center of the Earth, understand that, it is only going to weigh 0.25 newtons. If we went 3 times as far away, it's only going to be 1/9. However, it does not ever drop to 0. You always are affected by the Earth's gravity. You are always affected by the Earth's gravity. Even if you were in another solar system, you're technically affected by the Earth's gravity. Gravity affects everything. However, at that distance, it is so far away that the force is very, very small. Okay? But it is exerted through all of space. That's the interesting thing about gravity. It's exerted through all of space, and it's also exerted through space instantly at all times. So that's really kind of the weird part about it. So here's kind of shows you what happens. As you're closer, you've got a lot of force. As you get farther and farther away, that force is, hey, here it's a 4th, 9th, 16th, 25th, and so on. And we're dropping quickly as we're getting farther and farther away from the Earth. So you can see that, what happens. And that's why when we talk about astronauts out in space, technically, if you listen to NASA people, they don't talk about them being weightless. They don't say that there's no gravity, or maybe they say weightless, but they never say there's no gravity. They always talk about microgravity, because there is gravity out in space. Even the astronauts in the space station have some gravity affecting them. It's just so small that for us, it feels like we're just constantly falling. Okay, so let's say, suppose that an apple at the top of a tree is pulled by the Earth's gravity with a force of 1 Newton. If the tree were now twice as tall, would the force of gravity on the apple be only 1/4 as strong? Think about that. Nope, because remember, we're talking about from the center of the Earth, which is 6,370 kilometers. So you've got to go, in order to double that, you have to go 6,370 kilometers in the air in order for you to get 1/4 the gravitational pull. Okay. So let's talk about gravitational field. A gravitational field is anything that has mass can have a gravitational field around it. Think of like a force field, like a magnetic field or something like that. I mean, that's kind of what we're talking about here. And if you think of taking iron filings and sprinkling them on a magnet, you can kind of see how that lines up, and you get these fields. Well, the Earth kind of works that same way. You've got gravitational field lines, and as you get close to the Earth, you have that gravitational pull pulling you in. The closer you are, the stronger that field is going to be. So it'd be kind of something like this. These would be the gravitational field lines that you would see around the Earth, things pulling things in as you got closer and closer. Now let's talk about, this is where we get interesting. If we talk about inside a planet, let's say that, okay, here we go again. We talked about this earlier, but let's say we've got this hole drilled all the way through the Earth. And what would happen if you jump into that hole? Okay, so we fall in, and our acceleration at the beginning, hey, is equal to gravity, 10 meters per second squared when we're up here, right? But as we start to fall, if we're, quarter of the way through the Earth, it's only half of what it used to be. Now what happens is we've got a lot of the Earth above us. Well, guess what that's going to be doing? That's going to be pulling us up. And we've still got some Earth below us pulling us down, but we're starting to be counteracted by some of that Earth above us. As we get into the middle here, you've got just as much Earth above as you do below. So technically at that point, there's no acceleration whatsoever. Now you're already moving. You're moving pretty fast at this point, but there's no acceleration. And as I continue on, now that acceleration, it's going to start to slow me down, slow me down until I get out to here. And now my acceleration's back up to normal gravity force that we experience, and that's going to try to pull me back through the other way. Okay? So if I start at the North Pole, I'm going to fall, I'm going to gain speed till I get to the middle. I'm going to be going so fast then, and I'm going to overshoot and keep on going, and I'll come out in the South Pole. And this is what I like. This trip takes about 45 minutes. Now, in my personal opinion, I think that's what we should do. We should drill holes through the Earth and just make little cars that can travel through there. And man, you get from one side of the Earth to the other in 45 minutes. That's a heck of a lot faster than an airplane. I think that'd be great. So we need to come up with that so we can get from one side of the Earth to the other. Okay, so we've talked about most of this. No acceleration is if you're in the middle. If you're just out in the middle, let's say I could just teleport you right into the middle of the Earth. At that point, you would be, you would feel weightless in that if you're in the middle of the Earth like that, because you got just as much force pulling you here as pulling you here as pulling you here, pulling you here. It would be exactly the same as if you were weightless out in space, because all of the pulls cancel each other out. All right, here's a question. You stepped into a hole, bored completely through the Earth, and made no attempt to grab the edges at either end. What kind of motion would you experience? Well, what they're saying is it would be simple harmonic motion. In other words, you would go through, you would go back. You would go through, you would go back, you would go through. Kind of like a spring. Think if you pull a spring, you stretch it out, it kind of goes up and back, down and up and down. That's kind of the idea. That's simple harmonic motion.